So we're going to take a look here at oxyhemoglobin and the concentration of oxygen as it relates to oxyhemoglobin. The oxyhemoglobin is the reason why blood is always oxygenated and why blood is always red. The amount of redness that we see in the blood is dependent upon how saturated the oxyhemoglobin molecule happens to be. So the first thing we have to look at is hemoglobin. Hemoglobin is a globular protein made up of 2 alpha and 2 beta polypeptide chains with 4 iron molecules contained at the junction points between the alpha and beta polypeptide chains. There are 2 healthy forms and 2 disease-linked forms of hemoglobin referenced as A and A2. Sometimes the A is also referred to as the A1 hemoglobin molecule. If we look at things like the diabetic indices, where we look at what's referred to as A1C levels, what they're talking about is they're talking about methylations to the polypeptide chains or the carboxylations of the polypeptide chains. That's the C within the A1C levels. In terms of the diseased states, we have 2 types that are of importance as it relates to physiological complications that can arise for the patients. These are, in particular, the sickle cell hemoglobin molecules, where based off of pH balancing within the plasma and levels of oxygen relative to levels of carbonic acid within the plasma, we will see changes of the shape of the hemoglobin molecule leading to changes of shape within the erythrocyte itself, leading to the sickling that we will see with the sickle cell trait. Now, within the hemoglobin molecule itself, we have a region that has an iron molecule that's sitting in its ferric state, iron 2 state, which means that it's able to bind onto 2 distinct molecules of oxygen. And so each hemoglobin molecule has 4 irons, and each iron can bind onto 2 oxygen, which means that each hemoglobin molecule will be able to carry about 8 oxygen molecules to it. Now, we talk about it as a single hemoglobin molecule. However, you have to remember is that there are hundreds of thousands and millions of hemoglobin molecules per erythrocyte. The amount of erythrocytes that are in the plasma will directly relate to the oxygen carrying capacity for the individual. This oxygen carrying capacity is what's referred to as affinity. And that affinity is how likely is the iron molecule itself to bind onto the oxygen and stay bound to that oxygen. There are a host of factors that are going to impact this affinity in what's referred to as a right shift, left shift direction within the hemoglobin affinity curves. These factors include body temperature. The change of body temperature is going to directly change the solubility of the plasma, and it's going to directly impact the gas laws as it relates to the solubility issues. pH is going to impact the affinity. As I move towards an acidotic state, I'm going to start having competitive inhibition on the hemoglobin molecules, leading to a carboxyhemoglobin formation as opposed to an oxyhemoglobin formation. In the carboxyhemoglobin or the deoxyhemoglobin, we end up having, instead of oxygen binding onto the iron molecules, we end up having hydrogen binding onto the molecules. The last of the things that will impact is the affinity of the gases, and this is the concentration of gases within the plasma. And it has to deal with 2 things. It has to deal with the molecular weight of the gas and its relative solubility within the plasma. in which carbon monoxide has a higher affinity than oxygen, which has a higher affinity than carbon dioxide. This affinity of gases in the binding is why we have to worry about atmospheric conditions as relates to the carbon monoxide, and why if you happen to have gas heaters or a gas stove or range at your home, you need to have carbon monoxide monitors, because what ends up happening is that carbon monoxide will bind onto the iron region of the hemoglobin molecule and not allow for oxygen to bind onto. And it will lead to a reduced oxygen carrying capacity. And for those aerobic obligated tissues, will start to lead to the necrosis and apoptotic cycle due to metabolic interference. Within this hemoglobin affinity, we have a change of amount of oxygen being transported on the hemoglobin based strictly on the partial pressure of the oxygen within the vasculature. Now, even though we look at having a lower saturation of hemoglobin on the venal side, blood is always oxygenated. Not only is blood always oxygenated, blood is always red. The reason for blood always being red and blood always being oxygenated is because even though we have a lower partial pressure of oxygen, it doesn't go to zero. There is a second form of this iron-carrying globular protein that is found within muscle, known as myoglobin. Myoglobin is able to saturate at a much lower level of partial pressure of oxygen than the hemoglobin molecule and will stay saturated for longer periods of time. This is the myoglobin that we saw in the type 1 and 2A fiber types within skeletal muscle that allows for the continued aerobic metabolism during the shortened periods of time where we do not have constant perfusion. When we talk about the saturation points of oxygen within the oxyhemoglobin curves, what we have to remember is that 98.5% of all oxygen will be found bound, regardless of how much oxygen is there. 98.5% will be bound. 1.5% will be dissolved. It is that 1.5% that is going to do the diffusion. And so within this affinity shifts, we see greater affinity in the arteries and lower affinity in the veins. And part of this lower affinity in the veins has to deal with the change of partial pressures, but it also has to do with the competitive inhibition that we see with carbonic acid as it relates to the necessity to maintain pH within the plasma. The pressure differences that we see on the arterial sides and on the venal sides as it relates to affinity is what's going to allow for gases to move into and out of the capillaries within the tissues of the body. And this is based off of a couple of gas laws, Dalton's and Henry's law, as well as the diffusion principles governed by Fick's law. But we also have another law that's going to come into play as it relates to the affinity on the hemoglobin, and that is Charles's law. The affinity that we see within the hemoglobin molecule is going to dictate what type of hemoglobin we see, whether it's the oxyhemoglobin, the carboxyhemoglobin, the carbonoaminoglobin, or the deoxyhemoglobin. The deoxyhemoglobin is seen when we happen to have high amounts of acidosis going on. And this type of hemoglobin that we see is what's going to dictate the shifts that we see in the hemoglobin curve. And so what we start with is we start with our normal curve, where we have normal levels of acidity and the normal body temperature. If I happen to have a right shift, I am shifting away from my saturation points. If I happen to have a left shift, I am shifting towards my saturation points. So if I happen to have left shifts, I am more aphenic. This left shift we see with lower temperatures and with lower levels of acidity. Now, we don't want to be alkalytic, but we simply have lower levels of acidity that's going to shift leftwards, allowing for greater affinity between hemoglobin and oxygen levels. Part of this has to deal with the ability to saturate via solubility issues. The other part has to deal with competitive inhibition or lack thereof on the hemoglobin molecule. On the right shift, I am reducing my affinity. So even at very high concentration levels, I do not get full saturation like I should. I'm more apt to allow for oxygen to dissolve into the plasma. Not only am I more apt to dissolve into the plasma, there's more room in the plasma for oxygen to be found in. I also have competitive inhibition on the hemoglobin molecule based off of the need to clear carbon dioxide and the need to clear hydrogen ions from the plasma because of the acidosis that's going on. So let's take a look at some of these gas laws that are going to impact this hemoglobin curve. And we'll start with Henry's law, which is going to dictate the quantity of the gas that will dissolve in the liquid is proportional to the partial pressure of the gases across the membrane and its solubility. Carbon dioxide is 24 times more soluble than oxygen, which is why we see oxygen needing the molecule hemoglobin to carry it around, and why we see carbon dioxide in the plasma causing the carbonation of the plasma. The higher partial pressures at the tissues is going to dictate which direction gases will sublimate. Gases will leave the liquid and move from the liquid to the tissues, or from the tissues to the liquid. So let's take a look at what's going on in terms of the partial pressure as it relates to the overlying pressure and where gases are going to move from. So as we start reducing pressure, as the external partial pressure starts to drop, gases will start to move out of the liquid, moving out of the plasma and into the tissues. Start to increase pressure from outside. Insoluble gases will start to in tissues. This insolubility is why we have to worry about, for scuba divers or for people who are at high altitudes, changing pressure too quickly, as it can lead to nitrogen bubble formation because of the partial pressure and solubility issues of nitrogen. And so the other thing that we see in terms of Henry's law is it's dictating where gases are going to move to. So if I happen to have higher partial pressure of gas within the plasma and lower partial pressure of the gas out of the plasma, I'm going to have exchange from the plasma to the tissues. If that flips, I'm going to have exchange from the tissues into the plasma. And so how is carbon dioxide going to leave at the alveoli? It's going to leave in this fashion here, where we get high partial pressure of gas in the plasma moving into the alveoli, it's going to diffuse out. How do we get gas exchange at the tissues? The same exact way. There's higher partial pressure of oxygen in the plasma than there is in the tissues, and it's going to exchange outwards. The other gas law that we have to worry about here is Dalton's law. And Dalton's law is going to dictate the directionality in order to reach equilibrium of gases, in which we look at the total pressure of the gases and the partial pressure of the gases. And so gas diffusion across the membrane is always going to be from the higher partial pressure to the lower partial pressure in order to get partial pressure equality. Now, the pressures are going to change, however, the quantities and amounts of gases will not change based off of elevation issues. So people will say, oh, well, as I go up in elevation, the amount of quote unquote oxygen drops. The amount doesn't drop. The atmosphere is still going to be roughly 21% oxygen. It's just that the partial pressure is lower because there's less total pressure at higher elevation than there is at lower elevations. And this is going to lead to changes in the direction by which gases move. This same partial pressure issue in terms of Dalton's law is going to dictate which directions gases move relative to all of the gases in the solution. And remember, it's all of the gases in the solution. It's nitrogen and oxygen and water and carbon dioxide and any other gas that we see. Any change in the percentage of a single gas will impact all other gases there. Which is why, if you happen to be someone who is a runner, you do not want to run outside by major roadways once traffic starts to pick up. Because things such as other gases and carbon dioxide will increase, whereas the amount of oxygen will start to decrease by percentages within those areas. When we combine Henry's law with Dalton's law and with Fick's law, we get this net movement effect as relates to gas exchange at the alveolus as well as gas exchange at the tissues, in which oxygen will diffuse from the alveoli into the capillaries, and carbon dioxide will diffuse from the capillaries into the alveoli strictly due to partial pressure issues. The rate at which this takes place is based off of the differences between partial pressures, but the directionality stays constant. So what will impact the diffusion of gases? Boyle's law is going to impact it. The surface area for gas exchange is going to impact it. The molecular weight and solubility of the gases will impact it. The partial pressure across the membranes will impact it. Where we're going to have to combine various gas laws into the directionality, as well as the amounts based off of what's referred to as the driving pressures. We'll get a little bit more detail into this when we talk about gas laws as it relates to ventilation issues. But right now, let's go ahead and take a look at the issues of transport. So the transportation of gases is going to be impacted by Henry's law, which is going to indicate which gases we can see dissolved in the plasma and which ones are going to have to be bound. It's also going to indicate which gases will be able to diffuse based off of the directionality issues of partial pressure. Dalton's law is going to dictate the bulk flow of gases. And Charles's law is going to dictate the solubility of gases based off of the temperature that's there. And so let's put this all together and look at the oxygen transportation issue through the system. And once again, we're going to look at this based off of arterial blood and venal blood. Remember, it is not correct to talk about this as oxygenated or deoxygenated. There is no such thing as a deoxygenated blood. Exchange at the alveoli to the atmosphere. Oxygen will move inwards, carbon dioxide will move outwards, strictly off of partial pressure issues. Alveolus to capillaries. Oxygen will move from the alveolus to the capillaries. Carbon dioxide will move from the capillaries to the alveolus, strictly off of partial pressure issues. At the tissues, oxygen will move from circulation into the tissues, strictly off of partial pressure issues. Carbon dioxide will move from the tissues into the capillaries, strictly off of partial pressure issues. And so if we look at this in terms of circulation, if we look at the circulation, not just on the partial pressure, but based off of the saturation points, notice 1.5% of oxygen is found dissolved, 98.5% is found bound, and it doesn't change that much. 7% of carbon dioxide is found dissolved, 23% is found bound, 70% is found in the bicarbonate shuffle in between HCO3 negative and H2CO3. The only parts that are being exchanged are the dissolved parts. So based off of gases, we cannot call blood deoxygenated because there's always oxygen there, and we cannot call it oxygenated because there's always oxygen there.